Good morning, everyone. This is a makeup lecture for February 25, 2020. And today we're going to finish chapter number 3 and talk about these three last topics that we have here in 3.4 to 3.6. And those are elastic anisotropy, elastoplasticity, and viscoelasticity. And with this, we'll finish this chapter and then we'll move on to rock failure. And hopefully, we'll also see a little bit of that today. All right, so let's get started. The first thing that we're going to look at is elastic anisotropy. So far, we have said that most rocks, or that we have assumed a model in which we assume that the rocks are isotropic. And isotropy means that all the properties are the same in all directions. So no matter the direction in which you apply a load, you would expect in an isotropic rock the same deformation in that, independent of the direction in which you apply the load. And that's true for some materials, like, for example, steel, some very homogeneous ceramics, but it is not true for rocks. Rocks are not isotropic, they are anisotropic, and especially sedimentary rocks. And here I have one example. Let me pull it up. If we look at this figure here in the middle, number B, we see an example of a shale that has layers of sediments that corresponds to different types of sedimentation, and that layering induces anisotropy. And in general, with all sedimentary rocks, layers, either if they are fine at a few millimeters scale like this one, or bigger, they will induce rock anisotropy. And that anisotropy then means that the Young modulus is going to depend on the orientation in which you measure the rock property. And let me do a schematic of this here in the notes. Just give me one sec, I get this set up. So here we're going to deal with anisotropy, and particularly elastic anisotropy. Probably you remember also from your classes in reservoir engineering that permeability is also anisotropic, and the anisotropy is related to layering of these sedimentary layers. So here I'm just making a schematic of a sedimentary basin. Usually I can draw this cow a lot better, but here now I'm drawing with stylus, which is not very good. But the idea is that as time passes by, we have more sediments accumulate, and if there is no strong tectonic forces, then those are just going to remain horizontal. If there is no erosion too, those are just going to remain piled up. And because of the layering, we're going to see that the properties of these rocks are going to depend on whether you take some of these rocks and you apply a load in horizontal direction, or if you apply the same rock but now you apply a load on vertical direction. Let's see how that would look on the schematics that we have done and what we have learned about elasticity. If you remember, we measured the Young modulus by quantifying the change of stress related to a change of strain. And if you were to run a test on some of these samples, you will observe that if you test the rock which is in direction parallel to bedding, and this is this rock over here with the load in the direction of the bedding. In general, for most rocks, that will tend to be stiffer than if you were to apply a load perpendicular to bedding. There are several reasons for this, and they are associated with if you remember, averages in series and in parallel. In the case of the vertical loading, this will be an average which is in series. And if you had any soft layer within that pack, let's say, for example, that this is a soft layer and that one too. If you have soft layer in those will tend to take most of the deformation, and that's why this will look a little bit softer in vertical direction. So if we were to measure then the Young modulus, this would be the vertical Young modulus, this would be 1. And if we also do the same over here, this is going to be the horizontal Young modulus, and this is going to be 1, where, as we were saying before, in general for sedimentary rocks, the horizontal Young modulus tends to be bigger than the vertical Young modulus. And that will depend on the kind of rock, on the properties of those layers inside the rock. Let me show you an example of this, an action example, which it actually applies very well to problems that we have right now, for example, for unconventional formations. Here, I'm going to show images and results of a study in which there was a study of the stiffness and Young modulus of several source rocks that contain organic matter. So in this case, what you observe, I like that you pay attention to this picture, Eagle 4, number 1. You can observe the minerals, which are mostly, this is a thin section, which are mostly light colors, brown or white. But you can also observe thin layers of dark material. And sometimes there are layers, and some other times they look more like lenses. And also you can see that very clearly here in this picture, Eagle for number 2, and you can also observe it in this other one, Hainesville number 2. Those layers and lenses are kerogen. Those are organic matter. And organic matter tends to be a lot softer than the other mineral components like quartz or calcite and dolomite. And because of the lower stiffness of this organic matter, when you measure vertical Young moduli, which will be here in also in the screen in vertical direction, and horizontal Young modulus, which will be in horizontal directions, the same as in the screen, then you will find that the vertical Young modulus tends to be much lower than the horizontal Young modulus. And here you have an example of actually of those measurements, which are done very similarly to what you have done already in the laboratory. And let me zoom in this plot. A little bit more. All right, that's good. Here you can see that those measurements of Young modulus on vertical, in the vertical direction and the horizontal direction. The triangles over here are the measurements in horizontal direction, and the circles are the measurements in vertical direction. And each color represents a type of rock. So let's look, for example, at this rock, which is the red one with the field symbols. Here you can see that in this case, for the rock that had a percentage in volume fraction of clay and kerogen of about 40%, which is quite a bit. So that would mean like 40% of the entire rock in volume is composed of soft materials. Then the horizontal Young modulus is about 40 to 50 gigapascals, but the vertical Young modulus is lower than 20. So in this case, the anisotropy of this rock, if you were to divide the horizontal Young modulus to the vertical Young modulus, that would be higher than 2. And that means the rock is quite anisotropic. And let's take a look just at, let me see which rock that is, just to complete the picture over here. Let me see, where are the labels? All right, so that was one of those Hainville's one rock that we saw some of those the scene sections before. So again, the elastic anisotropy is caused in sedimentary rocks mostly by layering, and in this example we can see the effect of layering of the soft fraction of organic matter. All right, so in most of our programs, we are not going to incorporate anisotropy because it makes it a little bit more complicated. In real applications, when you get to work in some of these problems, you have to do this. I remember reading a paper that was, the title was something like the fatal assumption of assuming rocks are as isotropic. Well, that was a little bit probably too extreme in saying that why would be so bad to assume isotropy, but in general, when you go to real applications, considering anisotropy would be a good idea. And the way to do that, I'm just going to tell you here how to do it, would be to incorporate this anisotropy in these stiffness tensors that we have seen before. If you remember our stiffness tensors before, that were matrices of 9 by 9 elements, they had as input just 2 parameters. And in the ones that we saw in detail, they just had the Young modulus and the Poisson ratio. Well, those are just 2 independent parameters. If you consider an anisotropic rock, then there are 2 simplifications. You can consider that the rock is orthorhombic, like here on the left. And in that case, you will have 9 independent parameters. That means that the stiffness, it depends. There are 3 different stiffness, C11, C22, C33 in normal direction. And there are some other different 2 in the shear components and also in the off-diagonal terms. But that will basically mean that every time you change the direction of loading, your stiffness is going to be different. An example of that is a medium that it's layered like the one that we saw before, but also that also has fractures inside the rock. If we consider something a little bit easier, we can consider a model that just has 5 independent parameters, and that would be transverse isotropy model. And in that model, this is the one that is very popular because it goes a little bit beyond the simple isotropy, but considers a more realistic behavior for sedimentary rocks. And in this case, for this transverse isotropic model, it looks very similar to what we drew before, but just let me draw it again to make it clear. If we were to have a solid, with layers that are responsible for the anisotropy of the rock, then we will say that this solid, as long as it has an axis of symmetry, like this, let's say this is the axis number 3, and here, let me check my right-handed coordinate system. This should be direction 1, and this one should be direction 2. then in this type of system, we will consider that the vertical stiffness, for example, is C33, and the horizontal stiffnesses are C11 and C22. And because we consider this medium is isotropic with respect to the axis 3, then the stiffness in direction 1 and direction 2 are the same. And if you remember what we saw before, and we assume that this is a layer system, we find that in general stiffness in direction 3 is smaller than stiffness in direction 1. And how much that stiffness changes tells you what is the anisotropy of the solid. All right, so that was just a very brief overview of anisotropy. Just as a reminder, I like that you remember that the drugs are not isotropic. In this class, we're going to assume mostly isotropy, but that doesn't mean that that's correct. And many times you're gonna have to go to a more realistic modeling, including anisotropy, to improve your predictions of stresses in situ and what happens after you do something like drilling or completion or some other things in the subsurface. All right, so let's go now to the next topic. The next topic is permanent deformation. And before I go here, just let me remind you that I'd like to summarize these topics 3.4, 3.5, 3.6 as behavior real rocks, because real rocks are going to exhibit also this type of deformations and these anisotropic deformations. All right, so let's go to 3.5. And this is about elastoplasticity. And elastoplasticity refers to irrecoverable or plastic strains. And let me show this example that you have already seen. Here we have a typical experiment in which we subject a rock to axial loading and we measure the axial strain and radial strain. If you remember, we did loading paths, but we also did unloading paths. And those two are going to be different, and the cause of that is the irrecoverable strains that are caused during loading. During loading, and whenever the strains are relatively high in magnitude, like for example a few thousandths or close to 1%, as you get in this particular test, you're going to experience, or your sample is going to experience irrecoverable strains. And when those irrecoverable strains add up to the elastic strains, they are going to make your rock to look as if it were softer. And when you do unloading, most of the deformation is elastic, because when you unload the rock, you're not causing further damage. When you load it, you cause some damage. When you unload it, you do not cause further damage. And because of that, then that unloading young modulus many times, almost always, is higher than the loading modulus. And again, this is due to irrecoverable strains. I like that you notice from this plot that you can have irrecoverable strains before you get to the peak stress. Of course, when you get to the peak stress, you're also going to have large irrecoverable strains. For example, if we were to unload this sample after failure, let me do this schematic here, we would also have a large irrecoverable strain. So let's make a schematic of this again. And now I'm just going to draw the axial strain, the axial stress. When we do loading, we have irrecoverable deformations. If we were to unload this all the way, let me try to do that a little bit better, all the way to zero stress, then all of that will be irrecoverable deformation. If we load it again, most times it will go through the same path and then pick up the strain stress curve where it was left. And if you continue loading it, you might get to failure, big stress. And if you unload it, it will usually come back and have a irrecoverable deformation because it has already gone to failure. So now the recoverable deformation will be here. All right, so you may wonder why we need to consider these irrecoverable deformations. And they are important because when we measure Young modulus, we need to know what kind of Young modulus we measure and what that means. Our model of linear elasticity is very useful, but sometimes if we use it incorrectly, then it might not give the accurate predictions that we are looking for. And here I have one example to show you how these loading and unloading processes are important and why that would be important in some cases. And this is a case in which we measure the rock compressibility either during loading or unloading. And let me bring that to the screen. It is this case over here. Before I go there, let me see if I found the other figure. Here we're assuming that we have a reservoir in which we change the pore pressure. And when, for example, you lower the pore pressure as in depletion, you are loading a rock. But some other times, for some other applications, you may inject the fluid and rather unload the rock, increase the pore pressure and unload the rock. And that would be an unloading process. And you may expect from what we saw before that the loading compressibility is not going to be the same as the unloading compressibility. In general, the loading compressibility is going to be higher than the unloading compressibility, which means that the rock is going to look stiffer as you unload as if you load. And here, for example, I have results of some of these measurements in which we measure these compressibilities for a sand, and we see that the loading compressibility, which is here with field symbols in this figure number 4, it's 3 times and sometimes higher, 3 times or more than the unloading compressibility. So in this particular case, this was quite important for reservoir engineering because most times in the laboratory, the conventional measurement is the loading compressibility. And if you were to use a loading compressibility, which is a lot higher than the unloading compressibility, and if you want to simulate injection of a fluid, like for example in wastewater disposal, or if you're doing some EOR process, or if you are injecting carbon dioxide for environmental purposes, then you will underestimate quite a bit what is the increase of pore pressure in a reservoir because your compressibilities are quite different. And in this example, this is what you see over here. If you were to use a loading compressibility, you will predict a much lower increase of pore pressure than if you were to use the actual unloading compressibility. And here there is one more thing that I hope that that you remember that we discussed before the difference between uniaxial strain compressibility and isotropic compressibility. Those are not the same. And traditionally, in the oil industry, we have measured isotropic loading compressibility of rocks, and that tends to be a lot higher than the true compressibility of rock under reservoir conditions, which is a uniaxial. So in this case, an incorrect calculation of this compressibility can result in quite a big difference of increases of pore pressure. And these plastic deformations are also going to be there. And in general, the longer the time of the action that you apply on a rock, the more plastic strain you're going to have. The closer you are to the failure of the rock, also the higher the magnitude of that plastic strain is going to be. We'll get back to plastic strains later when we talk about rock failure. And the last topic that we're going to see today about linear elasticity and continuum mechanics and extension to realistic rock is time-dependent deformation. Time-dependent deformation, also called viscoelasticity, it's a theory that helps us to predict what is going to be the responsive rock with time. Let me skip this figure and go to the next one. Time is going to be quite important because rocks are not going to have just a one-to-one relationship with stress. Time is also important. And probably you remember from your solids class, I'm not sure you have seen it, but probably you have heard before about creep. Creep is time-dependent deformation when you have a constant applied stress. Let's look at this example. This is a rock here on the top left, which is subjected to effective stresses in all directions. In this particular experiment, the stresses are increased up to a certain point, and then that's held constant. And when stresses are increased, you will expect strains also to increase. And this will be related to the relationship that we have seen before between stresses and strain through stiffness. But in realistic rocks, we see that after you stop applying the stress and you maintain that stress constant, you stop the increase, but you maintain that constant, strains are going to continue with time. And those are the so-called creep strains. This means that rocks are going to deform after the stress is applied and if that stress is held for some time. And there are some rocks that tend to creep more than others. And one example of creep is an example related to drilling. And let me go down over here. I'll make this schematic. As you may know, many times during drilling, especially offshore, uh, we have to go through salt rocks. Salt rocks are very particular because they do not like to hold any shear stresses, and they will tend to deform with time quite a bit. So if you were to drill a wellbore in this section, and let me see if I can delete this. Okay, so now we have a wellbore in this section, and you have an open hole. Salts tend to creep quite a bit. So when the hole is open, all the weight of the rock and the stresses around the wellbore that we're going to see later on when we get to drilling, how they affect mechanics around the rock, they will make the salt to creep and tend to get into the borehole. And those would be caused by what we call the creep strains. As long as you have stress on the rock, the and it does not balance with the stresses on the wall of the wellbore, that's going to tend to creep. And if you leave the well with the, the uncase for a long time, this salt might finally creep and close the wellbore. A solution for that would be that as soon as you drill the wellbore, you case the wellbore, and uh, and that would be the solution for that problem. But if you don't, the wellbore is going to close because of the property of the rock to flow uh, with an applied stress. And salt rocks are an example of rocks that tend to creep quite a bit. Also, there are some other types of rocks, like for example, mud rocks that will tend to exhibit quite a bit of creep, and that's going to be very important because it's going to affect, as we just have seen in this example, drilling, but also can affect stresses, in situ stresses after a long time. One more example about creep is the case of a salt dome. I don't know if you guys are familiar with salt domes, but salt domes are structures that form under the surface in which um, let me see if I can get this drawing right. A salt layer is deposited, and because of the low density of the salt, it tends to rise. And as it rises, it breaks up through all the sedimentary layers on top. So here, oh, sorry about that. Just to make it a little bit clearer, what you're looking at is at a sedimentary basin in the subsurface where this is water, this is a fish over here, and all of these are sedimentary layers. Salt domes are very important for petroleum industry because next to the flanks of the salt domes, many times you have oil accumulations, and also because sometimes when you have to drill close to those, they are a little bit problematic. And this is caused by the same phenomenon of flow of a material, in this case a rock, with applied stress. In this case, the stress is applied by the loading and the weight of these sediments around the, the rock and on top of the salt layer that make the salt dome rise. All right. This is not the only phenomenon that we see related to viscoelasticity. In addition to this, we also see another type of expression of viscoelastic materials, which is sort of the opposite to what we see right now. So, and that's called stress relaxation. In stress relaxation, what we see is that if we apply now a certain strain to a rock and we keep that constant, the rock is going to opposed to that strain to an increase of with an increase of stress, in this case a deviatoric stress, the difference between sigma 1 and sigma 3. But over time, the material is not going to be able to hold that stress constant. That stress is going to decrease with time. And the reason for that is that the rock is internally failing at the microscale. Some grains are sliding with respect to each other, very tiny amounts, because they are subjected to stress. Some small cracks may propagate within the rock, and because of that, the material will get softer and it's not going to be able to resist to that stress, that high stress all the time, and that's going to decrease with time. And this phenomenon of this decreased stress with an applied strain is what is called stress relaxation. And this is quite important because what this is telling you is that the relationship between strain and stress is not unique and it depends in time. And because it depends on time, then it matters at what time after you apply this strain, uh, you measure the stress or you predict stress, because it's not going to be the same. And let's see an example of this. I hope you remember when we talk about tectonic strains. And we use a simple model in which we predicted what would be the horizontal stress with a tectonic strain. And let me come back to the notes. In this case, for example, if we have a, let's say, reverse faulting regime, if you remember, for reverse faulting, we had significant tectonic strains. This is going to be different than zero. And what the tectonic strain caused was the stress to the horizontal stress to be higher than the vertical stress. So let me plot this. Let's say that this is vertical stress over here, and that our horizontal stresses are somewhere over here. And I'm not going to draw the minimum horizontal stress just to make this plot a little bit easier. So if we have a tectonic strain in this case, which is pushing these layers, and I'm just going to draw this schematic just to remind you that we are meaning that to this sedimentary basin we are applying a loading in horizontal direction. If this is a viscoelastic material, with time this horizontal stress will tend to decrease, because real rocks are going to release some of that stress. And the difference between the maximum and the minimum, in which this case S1 is SH max and S3 is SV, is going to tend to be reduced with time. And as a result, the stress with time is going to be lower. So we may have cases, for example, in which we have a tectonic strain which is pretty high, but probably was pretty high 100 million years ago. And after 100 million years, some of that tectonic activity stopped or went into a different direction. And as a result of that, stresses may relax with time. And that stress is not going to be the one that acted or that was present 100 million years ago. And this also can happen in normal faulting as well. So let's consider a case now in which our vertical stress is here and that we have a layer around this depth which is actually a organic shale. And for some time, let's say that, let me do another color. I'll do it with the violet. For some time, the minimum, let me change that. It's too thick. Okay, so well, I'll use this one. For some time, the minimum principal stress was this one. Let me try to improve that. This is going to be the minimum principal stress. Now the difference between the maximum and the minimum is going to be this, where S1 now is going to be the minimum principal stress. S1 is going to be the vertical stress, and S3 is going to be the minimum horizontal stress. If we have an organic shale that has quite a bit of viscoelastic behavior, and let's say that the other rocks, they do not have that viscoelastic behavior, that means that with time, this stress is going to tend to be reduced. So let me, just to remind you, bring back this plot over here. This means that with time, as long as this strain is acting, these stresses are going to relax and the deviatoric or the difference in stress is going to get lower and lower. And if that's the case, then that means that in this section, the stress is going to change with time. And this is quite important because now we can see that probably some of our models that predict stress just based on elastic properties, if we're not considering this viscoelastic component, they might be wrong. And we can see there are recent studies that show that this is actually real behavior. And stress in some of these organic shales that exhibit quite a bit of viscoelastic behavior, they tend to have a horizontal stress which is much higher than what you would predict without this stress relaxation. And in other words, it means that the fracture gradient is higher and the pressure to do hydraulic fractures is higher too. And if the minimum principal stress gets closer to the vertical stress, that also means that some of your fractures may go from being just vertical to be horizontal when you do hydraulic fracturing, which changes things quite a bit and it's quite important. So we'll get also to talk a little bit more about this when we get to hydraulic fracturing, but by now I will leave it here with this example of stress relaxation. Let me check the time to see how we are doing. So 44 minutes, okay. So we'll just go a little bit more. And with this topic, we finish this chapter. There's just one more thing over here. related to viscoelasticity, and this is the capacity of viscoelastic materials to have a different Young modulus depending if you uh, load these materials slow or fast. And this is just one extension of the previous two phenomena, creep and stress relaxation. And it happens that with these viscoelastic rocks, if you will tend to load them very slowly, then they will appear softer as if you tend to load them very fast. And that's related to some of the properties that we said before. And this is quite important too from the point of view of measuring properties of rocks, because in the laboratory you measure Young modulus by loading a rock in a few minutes. You shouldn't expect that that value that you measure under those conditions is going to be the same as the same loading that you will achieve, for example, over the life of a reservoir that may be a few years. It's a very marked difference, a few minutes to a few years. And in general, rocks are going to tend to be a lot more compressible or a lot softer when you load them during a long time than when you load them very quickly. And that's something also very important to consider for reservoir engineering. All right, so there are two more topics over here, but we're not going to talk about them right now because we're going to see them as we move along with other problems. And those are pore elasticity and thermoelasticity. If you want to read those, just be welcome to, but get back to that later on. It's not that we're skipping them for the entire course, it's just that we're going to come back to that later with some applications. Okay, so now let's talk about chapter number 4. And in chapter number 4, we jump to a new topic, which is rock yield and failure. And now we're going to consider that rocks can not only deform elastically or with some variation of elasticity, as we saw like a little bit with plastic deformation or viscous deformation, but now we are considering and we are trying to measure what is the strength of rocks and how they fail and how we can use that to our advantage to predict, for example, wellbore stability or to complete reservoirs, like for example with hydraulic fracturing. Well, in the failure mechanics of rocks, it's very important to get to know what the material or what the rock is made of, because that's going to change how the rock fails significantly. It's not the same to have a formation which is made of an uncemented sand like this one on the far left, or to have a cemented sandstone, or for example to have a vaggy carbonate. Those are going to fail quite differently. An uncemented sand is going to fail mostly by sliding of the sand grains one to each other. Sometimes you could have cases in which the stresses are so high that the grains themselves they start to break. In the case of a cemented sandstone, failure is going to be related mostly to the failure of the cement at the contacts between the grains, and on opposite to that, in a carbonate, like in this example, this baggy carbonate, the failure is going to be mostly composed of fractures that link pores. So the failure behavior is going to change quite a bit depending on what kind of material we're dealing with. And we're going to see later that that's very important. If you, for example, have an already fractured material, also those pre-existing fractures are going to affect failure quite a bit. All right, so it's very important to take into account what the rock is made of, and it's going to be also very important to understand what is the size of that failure zone. It's not the same to consider the property of a rock at a very small scale, like in this example on the top left, in which we have an example of rock cutting at the drill bit. In most of these cases, we are failing the rock matrix of the rock, and we want to test or we want to understand what are the failure properties of that rock matrix. If we have a little bit, if we go a little bit bigger in size, like for example, to a wellbore, here you see this circle on the top right. It's a schematic of a wellbore, and around the wellbore we have the rock. Here we go into a bigger scale, and sometimes we may hit directly the rock matrix, and some other times also you can hit some other interfaces or some pre-existing fractures which are going to change the behavior of the rock. Well, these two on the top are relatively small scale examples of rock failure, but we also have also much bigger examples of rock failure. Here on the bottom left, we have an example of hydraulic fracturing. In hydraulic fracturing, that can take the size of several hundred meters, up to 1,000 feet or more for some fractures. We engage a volume of rock which is quite large. And in that volume of rock, we may have pre-existing fractures that are going to affect what are the overall failure properties of the rock. So in this image, you may think of this fractured rock as, you know, the like the Jenga tower made up of a bunch of sticks piled next to each other. Well, the mechanical properties of those wood sticks is one thing. When you put them all together and you consider the interfaces, the mechanical properties of the entire Jenga tower, that's a different thing, because now you have to incorporate what is the mechanical behavior of the interfaces. And with fractured rock masses is the same. As you go into larger scale, you need to incorporate the features that compose that those large scale properties, like for example, fractures or different layers. Those you need to consider all of those. And also you can go much bigger in scale to consider failure properties. In this case, on the bottom right, we have an example of reservoir depletion near Long Beach. In this oil field, the Wilmington oil field, there was significant depletion that caused compaction of this reservoir over a length, as you can see in the map, of more than 10 miles. So we're talking about a geomechanical process or a failure process that is in this case of a few miles, which is a lot bigger than what we see in the other images. And the size of the problem that we're interested in is what is going to define our failure properties. All right, so let's get started in talking about failure. And today we're just going to talk about tensile strength. And this is what you're going to see in the laboratory tomorrow. Remember that there is a laboratory tomorrow, and that you're going to do a Brazilian test. And this Brazilian test is going to measure tension, tensile strength, which is one of the three types of failure that we're going to see in this class. Tensile strength, shear strength, and then the compression or compressibility of the rock including plastic strengths. All right, so let's go to tensile strength. Probably you remember from solids this schematic. Here, this is an example of measuring tensile strength of a metal bar that is subjected to tension in the ends. As you increase the tension, the material starts to deform. In the linear regime, you can measure that proportionality, and that's going to give you your Young modulus. But if you pull too much, that's going to get up to a maximum. And that maximum is going to be, under tension, the tensile strength of the material. So these two words are quite similar, but remember they are not the same. Stress is not the same as strength. So strength is the maximum stress that the material can support under a given type of failure. So in this case, the tensile strength is the maximum stress, here indicated with this red arrow, that the material can support under tension. Well, this looks like a very simple test, but we cannot apply it as it is here for rocks, because it's quite difficult to get a rock to look like a rod, like a long rod. And even if we were able to do that, it's quite difficult to grab it from the ends, because if you want to grab it with some, let's say, steel jaws or something like that, you're probably going to do some damage to that rock already. So it is really not easy to do this with rocks. An alternative to that is to shape the rock so that you can pull from the ends without applying any compression on the sides, or without any type of jaws, or sometimes also you can use a cement to bond the rock to the ends, but then your cement has to be stronger than the rock itself, which it might not be easy to do. So an alternative for this is just to put the rock into a lathe and have the shape similar to the one which is in this figure, and also perform a tensile strength test. You can do this, but also it's not the most convenient test. But in this case, you will get the direct tensile strength of the rock. Again, you pull from the sides, you apply a tensile stress, the maximum stress that the material can support, that's going to be the tensile strength of the rock. In geomechanics, we have another type of test to measure tensile strength, and that's the Brazilian test. And this is the one that you're going to do in the laboratory. In the Brazilian test, what we do is we get a sample of rock, which is looks like a short cylinder, and you apply a load along the diameter. And this load applied along the diameter, what it's going to do is going to create tension at the center of the rock. And let me explain you why that's the case. So now we're getting into chapter number 4. And in chapter number 4, now we're going to talk about the Brazilian test. So let me do this schematic again. That should be an N, okay? Brazilian test. And well, okay, let me do it again. Brazilian test, okay. And as we were saying, we're going to test a rock which looks like a short cylinder, and the load is going to be applied in the load frame along the diameter. The result of applying this load along the diameter is going to be that those stresses are going to distribute along the rock non-uniformly. The compression, as you may expect, is going to travel from the top to the bottom, right? But it's not going to follow a straight path. From top to bottom, in the middle, it is going to follow a straight path. But these stresses, the compression stresses, are going to bend in order to take advantage of that surface and that volume of rock. So all of this is going to be compression. And because this is going to be compression, the compression is going to be bending, what that's going to create is a stress on perpendicular direction, which is going to be a tension. So in the middle of the sample, we're going to have a tension that goes in this direction, and as you go further away from the middle, these tension lines are going to be perpendicular to um, the compaction lines. And now if we'll take a look at the center of this sample, and we take an element there, in this direction we're going to have compression, but in this direction we're going to have tension. And what that is going to cause is that when the tensile strength of the material is meets the stress applied to the rock is going to fail here in the middle, and that crack is going to propagate to the top and the bottom of the sample. All right, so this is the schematic that it is over here, and you're going to do this in the laboratory. Remember to measure the length of the rock, the diameter or radius of the rock, and applying a constant displacement rate. You're going to load it, and the maximum load is going to give you, through an equation, what is the tensile strength. And that tensile strength is going to be equal to that maximum force divided by the length of the material times the radius. So it's a very, this is a lot simpler than the previous test that we were showing. And this is the one that we're going to do in the laboratory. And just to finish, here you have one example to determine what is the tensile strength. But just to finish here, I have a nice plot about typical values of tensile strength of rocks. In orange, we have sedimentary rocks, and here in red, an average for igneous rocks, and here in green, an average for metamorphic rocks. In general, sedimentary rocks have a much lower tensile strength than igneous and metamorphic rocks. And here, for example, I'm not plotting sand, but we know that sand, unconsolidated sand, has no tensile strength at all. So we also have materials with no tensile strength. So you're going to do this test tomorrow, Wednesday, and take a look at this graph after you do your test, and just try to see how strong your rock is, and to see if it's relatively strong or not, and if, I don't know, it reaches values close to 10 MPa or closer to 1 MPa. That's going to tell you more or less, combined with this plot, how strong the rocks that you were testing, how strong they are. Okay, so with this, we finish this makeup lecture for today. And for the next one, we'll talk about shear strength. All right, so that's it for today. Goodbye.